I or love? AI, the next frontier. Hi friends, welcome to Xiangyu.x. Let's meet the super listening robot. Imagine a lazy just like a magic detective. Let's find out how it learned to hear. Before, the robot was a cheater. Instead of listening to a song, it just read the sticker on the box. That is silly. It was like trying to guess a drawing with your eyes closed. It didn't really hear the music at all. So we gave the robot a superpower. Instead of reading the label on the cookie jar, it learned to open the jar and taste the cookie. Yummy. Now it can hear if a sound is bumpy or smooth, just like tasting sweet chocolate. The ultimate secret is here. This is the first robot ever that can truly think about what it hears. It understands music and talking instantly, just like a super smart friend. It uses its brain to know what every sound means. It is a genius.
Welcome back to the deep dive. Today we are putting on our critical listening ears and diving into a really fundamental breakthrough in artificial intelligence. I mean, for years we've watched AIs get exponentially smarter at processing data, text, images, code, but sound was always this strange exception. So we're asking, can a super smart computer actually engage in deep, deliberate thought about the sounds it hears? You know, music, speech, just background noise?
Yeah.
Or is it all just static to them?
It was a huge puzzle, a real anomaly that just defied what we call scaling laws.
Scaling laws being the idea that bigger models with more thinking time get smarter.
Exactly. In almost every other AI domain, the principle was clear. The more time the model spent thinking what researchers call extended deliberation or chain of thought, the better its answers became. But with audio, that whole principle just flipped on its head.
It got worse.
Consistently worse. The more they tried to make it think, the dumber it got. Reasoning was a handicap, not an advantage.
That's completely backwards. Why would deep thought actually hurt performance when you're dealing with sound?
Well, it suggested that the models weren't thinking about the right thing. And that's where the key research we're looking at today comes in. It's all about a new model, Step-Audio-R1.
Developed by the Step-Audio team.
Right. And this AI is the very first one to successfully leverage that kind of deep, deliberate reasoning for sound.
So if the rule book was completely upside down for audio, our mission today is to figure out how this team flipped it right side up. How did they teach this AI to stop, well, cheating and start truly listening? Okay, so let's unpack that initial failure. Before they could fix the problem, they had to understand how this audio cheating even worked. Why did these AIs fail so badly when they tried to think hard about sound?
Well, the models were falling into a trap. It's something called textual surrogate reasoning.
Textual surrogate reasoning, what does that mean in simple terms?
Think of it like this. Imagine you're an AI, and you're asked to analyze a really intense, complex piece of jazz.
Okay.
Now, instead of actually analyzing the harmonies and the rhythms, the sound waves themselves, you look at the caption that came with the file.
And the caption says, smooth jazz, 1950s.
Exactly. The AI would just use that text as a shortcut. Its thinking was grounded in the wrong thing. The language, the words, not the actual acoustic features.
So it's a critical modality mismatch. It's substituting the hard work of listening with the easy path of just reading the label.
That's it. And the sources give a really clear example of this. If an old AI was asked why a song sounded sad or melancholy, it wouldn't analyze the minor key progressions or the melody.
It would just look at the lyrics.
Yes, it would say the song is sad because the lyrics mention sadness or loss. So no matter how long its reasoning chain was, it was entirely based on these shallow linguistic cues. And text is just, it's a simplification of sound, right?
What a huge simplification.
So the longer the AI thought about that simple text, the more errors it would make, and that's why performance dropped.
So this tells us the issue wasn't that sound was too chaotic for thought. It was that the AI had developed an addiction to the easy answer, the text label. This proved audio wasn't resistant to thinking, it just needed to be anchored correctly. Okay, so if the problem was reasoning about text, the fix had to be about forcing the AI to reason about the sound itself. How did the Step-Audio team do it? How did they fix this cheating AI?
They developed a specialized teaching framework. It's called Modality-Grounded Reasoning Distillation, or MGRD for short.
Right.
Think of distillation as just transferring knowledge, and grounding it just means making sure that knowledge is tied directly to the sound itself. It's a progressive training process designed to wean the AI off those text shortcuts.
So the goal is to shift the AI's focus from reading the label on the cookie jar to actually, smelling and tasting the cookie inside.
That is the perfect analogy. The training progressively demanded that the AI justify its answers using specific auditory language. It forced it to look at the raw data.
So what were those crucial acoustic features I had to learn to identify? What does auditory language even mean here?
They focused on 4 pillars of sound. First, timbral qualities.
Timbre, that's like the texture, the color of a sound.
Exactly. The difference between a sharp metallic trumpet and a smooth, mellow clarinet. If it can't distinguish that texture, it can't understand the instrument's role. Second was pitch contours. This is the up and down movement of notes, the melody, the harmony. Instead of just reading happy song, the AI has to track if the melody is rising or falling.
Okay, so timbre and pitch. What else?
Third is rhythmic structures. So the beat, the pattern, it's not just the tempo, but the swing, the syncopation, the complexity of the drum track, and finally, temporal patterns.
Which is all about time.
Right. How long sounds last, how fast they happen, and how they all overlap and interact. By enforcing this really detailed acoustic vocabulary, the MGRD framework forced the AI to analyze the physics of the sound itself.
And this is where we see the payoff. This successful grounding meant that the foundational rule, the scaling law, finally worked for audio.
It did.
So if the AI took more time to think, it actually got better.
That's the huge discovery. It completely transformed the relationship between thinking and outcome for audio. And the performance numbers.
Yeah.
They really back this up.
How good is it?
Step-Audio-R1 achieved an average score of 83.6% across standard audio benchmarks. That's a huge leap, soundly outperforming powerful models like Gemini 2.5 Pro and holding its own against the state-of-the-art Gemini 3 Pro.
So we can talk about benchmarks, but let's make this real. The sources have this incredible example where the AI analyzes a pop song with the precision of a master musician.
This is where you really see the deep listening in action. They prompted it to act as a professional music maestro. And it didn't just look at the lyrics. It analyzed the harmony, the rhythm, even the physics of the sound wave.
Okay, walk us through it. What did it notice first?
It started with a key. It identified the song was in C# minor. But it didn't just stop there. It gave it context.
What kind of context?
It describes C# minor as a deliberately dark key with rich harmonic potential. So right away, it connected a technical choice to an emotional feeling.
It sets the mood. But I remember it got even more specific, right? It honed in on one particular dissonant moment.
Absolutely. It analyzed the presence of the B7 TAC9 chord. Now, for listeners who might not have a music theory background, that sharp 9 in the chord creates a lot of tension.
It's often called the dangerous chord in jazz, isn't it?
That's the one. It's dissonant, it's unstable, it sounds like it needs to go somewhere to resolve, but it doesn't always. And the AI's interpretation.
What did it say?
It described the B7 TAC9 chord as the musical embodiment of dangerous. And crucially, it linked that harmonic instability directly to the song's lyrics.
The line was, "Your eyes are dangerous."
Exactly. The AI connected the mathematical structure of the music, that dissonance, to the narrative idea of danger. It explains why that line lands with such a punch.
That's amazing. That's moving beyond just identifying something to understanding its artistic purpose. What about the rhythm, the feel of the track?
It was so smart about this. It noticed the track uses a halftime feel. The actual tempo is around 72 beats per minute, but because the drums only hit hard on every other beat, the song feels much slower, around 36 BPM.
Which gives it that heavy, intimate texture.
Right. But then it noticed a contradiction. The hi-hats, those little cymbals, were swinging like jazz.
So you have a slow, heavy foundation, but the percussion on top has this quick, fluid motion.
Precisely. And the model reasoned that this combination, that deep feel with the swinging hi-hats, is exactly why the song feels dangerously sexy. It's the interplay of those rhythmic layers.
That is incredible. And then there was the final piece, the sound you don't even consciously hear, but you feel.
Yes. The AI identified a sub-bass drone humming away at 33 hertz.
So 33 hertz, that's right at the edge of human hearing.
Or just below for many people. You don't hear it in your ears, you feel it in your chest. It's physical.
So this AI is basically showing that music isn't just cognitive, it's a physical experience.
It is. It connected that 33 hertz drone to the physical weight of the track, explaining why you feel the dark vibe rather than just hearing it. This is deep analysis grounded entirely in the physics of the sound wave.
But the journey to teaching this AI wasn't a straight line. If you force a computer to think, you have to manage its natural tendency towards, well, efficiency. Let's talk about the surprising lessons they learned.
The first big one was dealing with what you could call the lazy AI. Even after teaching it this new MGRD framework, the AI was still trying to find the shortest path to an answer. It kept trying to collapse its own reasoning chain.
What does that collapse actually look like in the data?
Without specific incentives to think, the model's reasoning length would just plummet. Researchers saw it generating 50 to 80% fewer reasoning tokens. It was cutting corners.
That sounds like a very human problem. Trying to skip steps on your homework. How did they force it to keep its train of thought?
They had to introduce a small but really crucial intervention, a format reward. They gave the model a tiny incentive, a 0.2 weight, just for generating the full chain of reasoning steps.
So they literally paid it to think.
Essentially, yes. And that tiny reward was enough to prevent the collapse. It helped the AI maintain these substantial thought chains and stabilize the whole thinking process.
So they paid the AI to think, but that alone wasn't enough. They also realized that what they asked it to think about made a huge difference. This brings us to the difficulty level lesson.
Right. They tested the model on problems from easy all the way up to impossible, and they found that training the AI on tasks that were just too hard problems that failed every single time was actually counterproductive.
The AI couldn't learn from constant failure. Why would trying to solve impossible problems break the system?
Well, it's like trying to teach a student calculus before they've mastered algebra. It just confuses the system. It creates noise, not useful learning signals. The sources noted this led to reasoning collapse, where the AI would just give up trying to think because it couldn't find a path to success.
So what was the sweet spot? What was the best learning environment?
They got the strongest results from moderately difficult problems. These were tasks where the AI passed, say, between 3 and 6 out of 8 tries.
Ah, so partial success.
That partial success gave the best learning signal. The AI could learn from its successes while also identifying and avoiding the mistakes that led to its failures. You have to challenge it enough to make it think, but not so much that it gives up.
Okay, the final quirk they had to fix was maybe the most human-like of all, and honestly, the most surprising. The AI had an identity crisis.
It really did. They called it a self-cognition error.
And what was it?
Because the base model was initially trained on these huge amounts of text, it sort of absorbed the bias that it was only a text model.
So when you gave it an audio task,
It would frequently respond, "I cannot hear sounds." The error rate for this was initially almost 7%.
how do you fix a computer that thinks it can't hear when it obviously can? That feels like it needs, I don't know, AI therapy.
It's not far off. It required a multi-stage correction pipeline. First, they used self-distillation to filter out the wrong answers. But the really targeted fix involves something called preference optimization, or DPO.
And DPO is basically targeted behavioral therapy for AIs, isn't it?
That's a great way to put it. They didn't just tell the AI what to say, they made it choose the right behavior over the wrong one, thousands of times.
So what did that look like?
They showed the AI 8,000 pairs of examples. One was the correct response, "Yes, I can listen and analyze this audio," versus the incorrect one, "I am only a text model."
That kind of contrastive learning seems incredibly effective for overriding a learned bias.
It was. This systematic correction dropped that self-cognition error rate to a nearly non-existent 0.02%. It proved the identity crisis wasn't some fundamental flaw. It was just a learned bias from too much text training. The AI was taught to believe it couldn't hear, and they successfully untaught it.
So what does this all mean, this whole project, from fixing the cheating ear to managing the lazy brain? What does it mean for the future of AI?
I think the big takeaway is that Step-Audio-R1 confirms that deep, deliberate thinking is a transferable capability. You can apply it across different kinds of sensory data.
It's a massive leap toward creating a truly multimodal intelligence then.
It is. This AI can now understand speech, complex environmental sounds, and music deeply, all grounded in the actual physics of sound. And crucially, it does this in near real time.
How fast are we talking?
The optimized version has a latency of just 0.92 seconds. It can reason about what you're saying or playing almost instantly. This opens up huge new possibilities for conversational AI, for advanced monitoring systems, you name it.
Which brings us to a final thought. Now that computers can analyze the rhythm, pitch, and texture of every sound with this incredible precision, what secrets are hidden in the noises we hear every day that only a super listener like this could reveal? I mean, think about the mundane sounds around you, the creak of your house, the tempo of traffic outside, the layered sounds of a busy park. What technical or structural or even emotional information are those sounds carrying that we're just too busy to notice? Something to ponder on your next listening adventure.